The moon's night lasts 14 Earth days. Imagine keeping a lunar base running in that darkness. NASA's answer? A nuclear fission reactor on the moon. The Fission Surface Power Project aims to deliver a small, lightweight reactor to the lunar surface within a decade. This nuclear battery would power habitats, rovers, and experiments, making a permanent human presence possible. But exporting nuclear technology to a pristine world raises serious questions. Space is already dangerous. Radiation, extreme temperatures, micrometeoroids. Add a nuclear reactor and the risks multiply. We've seen nuclear accidents on Earth, where help is nearby. On the moon, help is days away. Is this really our best option, or are we risking disaster for the sake of progress? The choices we make now will define humanity's future in space. Building a nuclear reactor on the moon could be a giant leap or a catastrophic stumble. Before we light that fuse, we need a serious conversation about the consequences. Are we being visionary or reckless? The stakes couldn't be higher. NASA's Artemis program isn't just about visiting the moon, it's about staying. The plan: a sustainable base camp near the lunar South Pole, a hub for science and a launch pad for Mars. This vision demands industrial-scale power. Enter the small fission reactor, 40 kilowatts of continuous electricity, enough to run life support, rovers, and resource extraction. Designed to last a decade, it's the heart of Artemis. Solar power can't bridge the 2-week lunar night. Batteries would be massive and complex. NASA and the Department of Energy see nuclear as the only practical solution. But launching, landing, assembling, and activating a nuclear reactor on the moon is fraught with risk. Every step is a high-stakes gamble. The Artemis program is already a monumental challenge. Nuclear power raises the stakes even higher. Is this technological leap worth the risk? The moon is the playing field, and the consequences of failure are enormous. We must weigh ambition against caution. Why is NASA so set on nuclear? 3 reasons: power, density, reliability. A small amount of uranium delivers massive energy, ideal for costly space launches. Unlike solar, a reactor works through the long lunar night and in shadowed craters. It provides constant, predictable power, crucial for life support and science. NASA also sees this as a test run for Mars, where solar is even less reliable. Proving nuclear tech on the moon could pave the way for Martian missions. From NASA's perspective, the risks are manageable with careful engineering. They argue nuclear is essential for real, sustainable off-world settlements. But are we underestimating the true cost of failure? The margin for error is razor thin. The first danger isn't on the moon, it's here on Earth. Launching a nuclear reactor means strapping enriched uranium to a rocket. Rockets fail. A launch accident could scatter radioactive material over a wide area. NASA plans tough containment, but no system is foolproof. Even after launch, landing on the moon is risky. Crashes happen. A failed landing could turn a lunar site into a radioactive exclusion zone. History warns us. In 1978, a Soviet nuclear satellite crashed, spreading radioactive debris over Canada. A lunar reactor would be larger, with consequences lasting millennia. The journey to the moon is packed with opportunities for disaster. Before the reactor even powers up, the risks are real and lasting. Are we prepared for the worst-case scenario? The cost of failure could be catastrophic. Suppose the reactor lands safely. New problems begin. The moon's environment is fragile, especially the water ice in shadowed craters, vital for science and future astronauts. Reactors generate waste heat, which could warm nearby soil and cause ancient ice to vanish into space. Radiation leakage, even if minimal, could interfere with sensitive instruments and contaminate the lunar environment. At the end of its life, decommissioning a reactor on the moon is far harder than on Earth. The likely solution? Bury it. creating a permanent nuclear waste dump. We risk turning the moon into a hazardous junkyard before we even understand it. Is this the legacy we want for our first off-world outpost? The environmental cost could be irreversible. Once contaminated, the damage lasts for generations. Are we repeating Earth's mistakes on a new world? The moon deserves better. Building a reactor for the moon is an engineering nightmare. Lunar dust is sharp, abrasive, and gets everywhere, destroying moving parts and seals. Temperature swings from 250 degrees to 280 degrees stress materials to the breaking point. Maintenance? Nearly impossible. Astronauts in bulky suits or unreliable robots must handle repairs. The reactor must be nearly maintenance-free for a decade, an almost impossible standard. Every component must be custom-built for vacuum, low gravity, and extreme conditions. Unknown failure modes lurk in every system. A single crack or leak could mean shutdown or disaster. We're building a one-of-a-kind machine where failure isn't an option. The complexity is staggering, and the margin for error is tiny. No one has done this before. Are we ready for the technical unknowns? The risks are as great as the ambition. If nuclear is so risky, what about solar? Solar power is proven, used on satellites and the International Space Station. The main challenge, the 2-week lunar night. But some lunar peaks near the South Pole get sunlight over 90% of the year. Tall solar masts on these peaks of eternal light could provide nearly continuous power. Battery technology is advancing rapidly. Future systems could store enough energy for brief darkness. Regenerative fuel cells offer another solution. Store solar energy as hydrogen and oxygen, then recombine for power at night. Solar systems are modular and scalable. Expand as the base grows. No radioactive risk, no hazardous waste. At end of life, solar panels are just metal and silicon, not a nuclear problem. Solar is cleaner, safer, and more adaptable. Why not choose the safer path? The sun offers a brighter solution. Solar isn't the only non-nuclear idea. Power beaming satellites in lunar orbit collect solar energy and beam it down as microwaves or lasers. Continuous safe power for the surface. The technology exists in prototype form and could scale to power multiple bases. Another idea, use the moon's extreme temperature differences with thermoelectric generators. These devices turn heat gradients into electricity, an area of active research. A diverse energy mix, solar, storage, beaming, thermoelectrics, could create a robust, safe lunar grid. Nuclear fission is just one option, and the riskiest. Innovation, not risk, should power our lunar future. The moon deserves 21st century solutions. The moon is a symbol of beauty and inspiration. The Artemis program lets us make it part of our story, but with great responsibility. A nuclear reactor risks catastrophe, launch accidents, lunar contamination, impossible maintenance, and nuclear waste. Proponents say the rewards justify the risks, but safer, cleaner alternatives exist. Advanced solar and power beaming can deliver the energy we need without the nuclear baggage. The decision is philosophical. What kind of explorers do we want to be? Will we repeat old mistakes or choose a wiser path? The moon has waited billions of years. Let's wait a little longer for a power source worthy of our aspirations. The risk is simply not worth the reward.